Welcome to the Proton Guru video practice for topic 7.5. These problems will give you practice on introductory topics in NMR spectrometry. Some brief and straightforward reading to get you ready for these kinds of problems can be found in the Organic Chemistry 2 Primer 2019 by Professor Houjeiry in lesson 7.5. You can also find additional chemistry videos and information on how to match up those videos to your course's textbook at protonguru.com. Our first problem asks us how many peaks each of these compounds will exhibit in a carbon-13 NMR spectrum. And in order to appropriately address this question, we need to be able to recognize symmetry elements in these molecules, and we need to know that the spectrometer will not see any of the other nuclei other than the carbon-13 nuclei when we are doing a carbon-13 NMR spectrum. So the carbon atoms in this first molecule are only these. We don't have to worry about the spectrometer seeing the O or the H's or the nitrogen. This molecule has symmetry down this vertical axis. So this carbon and this carbon will be the same as one another, and that will give us one signal. This carbon and this carbon are also related by reflection through that symmetry plane. And then we have this carbon that's laying on the symmetry plane that's unique. And then we have this carbon here at the bottom that I'm putting a square around. So we should have 4 signals for this molecule. The next molecule has no such symmetry plane, so each of the carbon atoms in that molecule will provide a unique signal in the NMR spectrum. We should see 5 signals in the carbon-13 NMR spectrum. This next molecule has 4 carbon atoms in its structure. This one is unique, sitting in the center, but each of these 3 carbons in the methyl groups will be equivalent. And that might be a little bit easier to see if we draw out the molecule like this. If we were to hold a model of this molecule by this bond and rotate around that axis, we can see that we could rotate and interconvert each of these 3 positions. So we will only see 2 signals in the carbon-13 NMR spectrum for that molecule. In this fourth case, we have 3 carbons. There is a plane of symmetry right here, so that we have a unique carbon that lies on that symmetry plane, and then these 2 carbons at the ends are related by that symmetry, or by simply flipping the molecule over. So there will be 2 carbon NMR signals for this molecule as well. In this epoxide, we can also see a plane of symmetry cutting through this oxygen and bisecting this carbon-carbon bond. These 2 carbons are related by that symmetry plane, as are these 2 carbons coming out of the plane towards us. So again, we should see 2 carbon NMR signals for that molecule. If we do the same type of analysis for many of the same molecules, but now we're asked about how many signals each of these will exhibit in the proton NMR spectrum, now we're only looking at the protons, so all the hydrogens in the molecule. So if we start by filling those in, we can see that we should have a signal number 1 for that proton, another signal for the protons on the nitrogen. Now, in the previous problem, we identified a plane of symmetry here, and that, of course, will relate this hydrogen to this hydrogen by symmetry. So those 2 will provide another signal together. We'll call signal 3. This proton and this proton are also related by symmetry across that plane, and that will give us the 4th proton NMR signal. So that would give us 4 signals in the proton NMR spectrum. So now we move on to this second molecule, and again, it's a good idea to fill in all the protons, and now we can identify how many signals we should get for this compound in its proton NMR spectrum. Rotation around this bond will allow these protons to interconvert with one another, so all 3 of those H's on the methyl group are equivalent to one another, and they will give us our first signal. Likewise, these 2 H's on the same carbon are identical to one another. They're magnetically equivalent. That would give us a second signal. These 2 H's would give us a third signal, and all 3 of these together would give us a 4th signal. In the previous problem, we saw that rotating this molecule around the carbon-chlorine bond axis leads to interconversion of the methyl groups. So each of those CH3 units is chemically and magnetically equivalent, and each of those 3 would then provide a single signal altogether. If we take a look at the 4th molecule and fill in its proton, we have these sets of protons, and there is a plane of symmetry cutting through this molecule. These 2 H's are equivalent to one another. That's going to give us 1 signal. And then the CH3s at each end are related by that symmetry and therefore they will produce all one signal. So we get 2 signals total for that molecule. This final case is more tricky. We have a plane of symmetry right here, and we can fill in our proton, and we see that these 2 H's are related by symmetry, but the H's on the same carbons that are away from us on these hash lines are not equivalent to these H's that I've circled here that are on the wedge lines, because these H's that are circled are cis to this bromo group, whereas these H's that are pointed away from us, they are trans to that bromo group. So they are not related the same way to the other pieces on the molecule. So I'll get 1 signal for those H's that are pointed towards us on those 2 carbons, related by symmetry, and a second signal for these hydrogens that are trans to the bromine. And then the H that's on the same carbon as the bromines will give us a third signal. So we will overall get 3 signals in the proton NMR spectrum for that molecule. Now we'll take a look at several aromatic compounds and evaluate how many signals each of these should have in the carbon-13 NMR spectrum. For benzene, if I just rotate this molecule in 1/6 increments, 60 degrees at a time, I can see that I can interconvert any of the carbons with any of the other ones just by rotating the molecule around. So we'll only see 1 signal in the carbon NMR spectrum for benzene. This compound, which is called mesitylene, has the ability to interconvert by rotation of 120 degrees at a time. So each of the methyl groups will be equivalent to each of the others by simply rotating the molecule around. So those will give us a signal. And that same 120 degree rotation will interconvert the carbons to which the methyl groups are attached as well. So all 3 of these carbons with the methyl groups coming off will combine to give us a second signal. Likewise, these carbons, which have protons attached to them, can be interconverted by simply rotating the molecule by 120 degrees. So those that I've drawn triangles around are equivalent to one another, and they together will give us a third signal. And that now accounts for all the types of carbons in this molecule. We should get 3 signals. If we look at this third molecule, which is called orthoxylene, we can easily identify a plane of symmetry there. So the 2 methyl groups are equivalent to one another, related by that symmetry, and that will give us 1 signal. The carbons to which the methyl groups are attached are also related by symmetry, and those will give us a second signal. These 2 carbons are related by that plane of symmetry as well. That will give us our third signal. And then these 2 carbons are also related by that plane of symmetry, and that will give us our 4th signal. And now we've accounted for all the carbons in the molecule, and we see that we should get 4 signals. In this next molecule, we actually see that we have 2 planes of symmetry that are easy to identify. So if I take a look at this carbon, for example, it's the same as this carbon because they're related by that symmetry plane. But this carbon is also the same as this carbon because they're related by the vertical symmetry plane. And then this carbon is the same as this carbon because they're related by the horizontal symmetry plane. All 4 of those carbons together are equivalent, and they will all together give you 1 signal. If we redraw that horizontal plane of symmetry, we can see the 2 methyl groups are related by symmetry, so together they'll give us a second signal, and these carbons to which the methyl groups are attached are also related by that horizontal symmetry plane, and they together will give us a third signal. So in the carbon-13 NMR spectrum, we'll only see 3 signals for that molecule. Another piece of information that we can get from NMR spectra will be the multiplicities of the different signals. And this will tell us something about how many NMR active nuclei are on adjacent sites. Now in this case, we're asked about the multiplicities of the signals in a proton NMR spectrum. So it might help to draw out the protons, and we can rotate around that carbon-chlorine bond to interconvert these methyl groups, as we've seen in previous problems in this homework. So we'll only get 1 signal attributable to all 3 of these methyl groups, and we'll call that set A. Now if you look at the carbon that is the neighbor to those methyl group carbons, this carbon does not have any protons on it. And remember that the multiplicity equals n plus 1. And here n refers to the number of protons, because we're talking about proton NMR, on this adjacent neighboring carbon. So n is 0. 0 plus 1 is 1. So that means that we should see a multiplicity of 1 is a singlet, And a singlet will look like this in the spectrum. So we should just see one simple peak. Well, let's consider a slightly more complicated case. Here we have this ketone. And since we're asked about the proton NMR spectrum, we should draw out all of the protons. And color-coded here, we've identified 3 distinct sets of protons, each of which will give you a signal. So we should get 3 signals for this molecule, and we're going to dub them A, B, and C for the red, black, and blue sets of protons, respectively. If we take a look at set A, we look at the neighboring site, which has a carbon right here. There are no protons on that neighboring site. And remember, the multiplicity equals n plus 1. N is 0, so multiplicity is 1. A multiplicity of 1 leads to a singlet in your proton NMR spectrum. Now if we move on to signal B, those protons are on this carbon. When we look at the neighboring site, how many protons are here? 0. How many protons are on this neighboring carbon? 3. So now M equals n plus 1. N is 3. So the multiplicity is 4. And finally we come to proton set C. If we look at the only neighboring carbon, it has 2 H's on that neighboring carbon. Multiplicity is n plus 1. Here n is 2, so the multiplicity is 3. A peak with a multiplicity of 3 is called a triplet. And if you look in the primer, you'll see the shapes of these particular peaks given here. So your NMR spectrum should contain peaks of these 3 particular shapes. And now we'll move on to an even more complicated case. You're again asked for the multiplicities for all the signals attributable to protons in the proton NMR spectrum for this compound. Again, as soon as you see which type of nucleus you're asked to analyze for, you'll want to draw all of those in. So we fill in all the protons in this case. Then we have to assess how many unique sets of protons there will be, therefore how many signals we'll get. So in this case, we see that these 2 methyl groups are equivalent by rotation around this carbon-oxygen bond. And then we have signal B, that's unique, it's the only CH. Signal C for the CH2 that sits in between the O and the carbonyl unit. Signal D, which sits between the carbonyl unit and a methyl group. And signal E, which is the methyl group at this far end. So we should see 5 signals in the NMR spectrum, and we need to figure out the multiplicity for each of those signals. If we first look at A, and we look at the neighboring sites, the neighboring carbon here only has 1 proton. Multiplicity equals n plus 1, and a peak that has a multiplicity of 2 is called a doublet. So protons, we've labeled A, should give us a doublet in the proton NMR spectrum. And now we move on to proton B. Proton B is on this carbon. If we look at the neighboring carbons, there are 2. This is not a carbon, this is an oxygen, which together have 6 protons. The multiplicity is then going to be 6, the number of neighboring H's, plus 1, which equals 7. An NMR signal with a multiplicity of 7 is called a septet. Now we look at signal C. Well, these protons that give us signal C are sitting on this carbon. That's not a carbon, therefore we only have 1 neighboring carbon, and it has 0 protons on it. So the multiplicity for signal C is n plus 1. Here the n is 0. The multiplicity is 1. A signal with a multiplicity of 1 is called a singlet. And now we move on to proton set D. Well, those are sitting here, so we look at the neighboring sites. There are 2 carbons that are neighbors. This one has 0 H's. This one has 3 H's, so that's a total of 3 neighboring H's. The multiplicity therefore is 3 plus 1. That's the n plus 1 in the multiplicity equation. So the multiplicity is 4. And an NMR signal with a multiplicity of 4 is called a quartet. Finally, we can go to our final set of protons, E. They sit on this carbon. Look at the neighboring carbon, and it has 2 protons on it. So multiplicity is those 2 neighboring protons plus 1. Multiplicity of 3. And an NMR signal with a multiplicity of 3 is called a triplet. If we were to take a proton NMR spectrum for this compound then, we would see a doublet, a septet, a singlet, a quartet, and a triplet.